Hello again to the Project Amor, ICMI Awardees Multimedia Online Resources. In the title of this unit, I promise to tell the commognitive story of the learning of mathematics. The first 6 modules might have seemed like a mere preparation for this storytelling. You have spent most of our time defining the basic notions of mathematics and mathematics learning. However, well-defined keywords with their built-in assumptions about what there is and how the different elements are related to one another already constitute a significant chunk of the story I wish to tell. Indeed, key concepts are theories in a nutshell. The rest of the theory will be derived from this and from what can be observed in reality. In the final modules, I am supposed to do precisely this, to elaborate the story of mathematical learning beyond what has already been told by means of definitions. In the previous 7th module, I focused on the societal historical learning of mathematics. In this closing module, I will try to do the same for individual ontogenetic learning, the kind of learning that happens mainly in schools. More specifically, while concentrating on ontogenetic development, I will do here what I did in the case of societal historical learning. I will attend separately to object level and meta level learning. And like before, this later level of learning will attract most of our attention. After discussing the societal historical learning of mathematics in Module 7, we are now turning to the question of how such development happens in the mathematics classroom. Here, the learner's task is to join the community of the historically established discourse known as mathematics. The student will do this by gradually individualizing the discourse, that is, by turning it into her own and making it available to her as an optional medium for her communication with herself, that is, for thinking. The currently popular view is that the best way to individualize mathematical discourse is to try to reinvent it. Called constructivist, this principle is often justified by evoking the names of 2 hugely influential theoreticians of human development, Jean Piaget and Lev Vygotsky. The underlying assumption is that reinvention, especially if carefully guided by a skillful teacher, is almost always possible, even if it is not always feasible. If it was so, individual learning would kind of replicate its historical societal version, and I would not have to add much to what has already been said in the previous module. But is it so? Let me look at each of the 2 levels of learning separately, starting with object level learning that, to refresh your memory, leads to an expansion of the theory of stories of already existing objects. In this case, the new stories you are going to tell will be obtained by deduction, and their production is thus a matter of logical necessity. Thanks to the regulatory impact of logic, you can indeed investigate the objects that populate your mathematical universe on your own, without fearing that your stories would turn out significantly different from those told by competent participants of this discourse. This, of course, provided that in the process of storytelling, you adhere to the rules of logic and make no mistakes. If so, in the case of object-level learning, the answer to the question, can students learn by reinventing mathematics, is yes, they can, at least in principle. Let us now have a look at meta-level learning. This time, not just theory, but also the rules of the game that the whole discourse is supposed to change. As I argued when considering societal historical learning, this kind of transformation is a matter of contingency, not necessity. To say it differently, mathematical objects and meta rules of mathematics are historically established conventions. Rather than being necessitated by rules of logic, they result from the fact that, for one reason or another, mathematicians opted for a particular possibility out of many. Introducing a new mathematical object involves human judgment and volition. The reasons for this kind of decision cannot be clear to mathematics learners before they can operate on the objects and experience their advantages firsthand. If so, in the case of meta-level learning, reinvention, although theoretically possible, is highly unlikely. This completes my answer to the question in this slide's title. But now another query offers itself. If, in the case of meta-level learning, reinvention is not a viable option, what is? How can this special type of learning happen? What is its plausible mechanism? The first thing to note when addressing the question is that when you are expected to transition to a new discourse about a new kind of mathematical object, you face paradoxical requirements. The paradox stems from the fact that mathematical objects, unlike rocks and animals, do not wait for us out there to be talked about. They come into being as we are telling stories about them. This may sound as unlikely as the claim that an aircraft is being constructed while airborne, with the constructor already sitting in it and flying. Indeed, to construct a new object, the learner has to participate in the discourse about it. But to participate in the discourse, she has to have already constructed the new object. She is entangled here in a veritable vicious circle, and it may be one of the principal reasons she may fail in her attempt to access the target discourse. This vicious circle has not been acknowledged in traditional mathematics education research. Whereas school curriculum is replete with meta-level transformations, these critical junctures and their paradoxical nature remain mostly invisible even to those who teach. Although the teachers certainly made this transition themselves at one point or another, it was a long time ago, and they are now oblivious to the pains this change caused, or even to the very fact it ever took place. Thus, when your further progress requires conjuring a new mathematical object, there may be nobody to help you out of the entanglement. In the view of this, it is unsurprising that many students drop out from participating in mathematics somewhere along the way. In fact, it is the frequent success of mathematics learning rather than its failure that should make us wonder. Indeed, how can students ever cope with the circularity? How do they break out of the vicious circle? Let me complete this part of meta-level learning by outlining a possible answer to this last question. As I stated, the newcomers to a historically established discourse should not be expected to become participants of this discourse on their own. They have to be exposed to the new discourse by long-time members of this community. Indeed, without such an exposure, the newcomers have nothing to come to. What does all this mean for how the meta-level learning may begin? To even start thinking about, say, negative numbers, the student has to be given an opportunity to observe the old-timers who can demonstrate to her what this discourse is all about and how it works. This, however, is only a necessary condition for the required meta-level learning. As argued before, mere exposure is insufficient for bringing her into good contact with the new mathematical object. Her journey toward those objects can begin only with what I call here reflective imitation of the old-timers' actions. Let me explain. Reflective imitation means emulating expert participants' actions while also making a sustained effort to figure out their reasons for doing what they are doing. After a period of reflective imitation, the student, if successful, we'll arrive at a good sense of the new object and of its being an inextricable part of the rest of the mathematical universe. All this will happen gradually. Imitating somebody else's actions cannot yet produce full-fledged routine. The baby form of routines may be called ritual. To understand its nature and its subsequent maturation, it is not enough to consider it in isolation. For this, we need to look at routines as parts of a greater whole, the system of routines. A useful analogy here is that of the need to relate to the whole human body while studying the nature and functioning of our heart or liver or any other of our organs. As you may remember, in the case of routines, the system can be presented as a network, the network of routines, or R network for short. This network can be thought of as composed of tightly interconnected records or memories of our previous actions, of your previous actions, thus of all your routines. This structure is comparable to a system of roads connecting different places. Like road system, R networks are dynamic structures that may evolve with almost any of your actions. Depending on the frequency with which you take different routes, some parts of your R network are more stable than some others. I will now take a closer look at a fragment of one anonymous R network presented here as a directed graph. The edges of the graph take the form of arrows that symbolize procedures. Every arrow originates in a vertex shown here as a small green circle. Each such vertex represents a task. In the present context, it is useful to think about the task as the set of all task situations that can count as each other's precedent, whereas the procedure that originates in this task is the set of all its implementations, performances you have ever done. Together, the edge and the vertex represent a routine. The recursivity of routines expresses itself in the fact that two or more routines can be connected to create a new one. And what is the nature of this connection? One type of connection is exemplified here. Routines A and B are seen as vertically connected or bonded because the performance of A yields a product necessary for the performance of B. In this situation, the product of A constitutes the defining part of B's task. Think, for instance, about the routine of bringing two fractions to the common denominator that, when connected vertically to the routine of adding two fractions with the same denominator, becomes a routine for adding any two fractions. Another type of connection, called a horizontal bond, occurs when a bunch of procedures, such as C, D, E, and F here, arrive at a single vertex, that is, when the procedures share the output set. This type of connection indicates that the same product can be obtained in several different ways. Think, for instance, about finding a minimum of a function by operating on either the algebraic, the graphic, or the tabular signifier of this function. This example clarifies why creating this type of connection is often an expression of meta-level learning, of the emergence of a new mathematical object that ties together several previously existing objects. To summarize, a fully fledged and truly useful or productive routine is one with rich connections to other routines. The tighter the bonds, the more useful the routine. Now, it is natural to ask whether a useful, productive routine may emerge just as a direct result of reflective imitation. Well, every performance of a routine, even if just imitated, leaves a mark within your R network. The more you travel this route, the greater your proficiency in the imitated procedure. In the graph, the road building process would express itself in the gradual thickening of the procedure representing arrows, as you can see here. Yet the thickness of the line does not by itself imply the productivity of the routine. Whether the routine is a ritual depends on its localization within the network. If it is unconnected and isolated, as is this one here, it is a ritual. In other words, the ritual may be seen as a road that leads to nowhere in particular. You still take this road from time to time, but only for the sake of exercise or for the sheer pleasure of strolling along it, which intensifies if you are doing this with others. To put it still differently, your routine will be described as a ritual if you are unlikely to initiate the procedure on your own, and you do it only when explicitly required to do so by others. The second earmark of ritual is that you judge your success in using this routine by social rewards you get for its performance, rather by a tangible, potentially useful product of your efforts. The social reward will come in the form of the approval by significant others or as an avoidance of a punishment. Since only well-connected routines are truly productive, thus useful, you cannot satisfy yourself with rituals. After a period of reflective imitation, you need to work hard to bond your rituals to a well-developed R network. The process of productivization or productization will be gradual. A gradual objectification of the discourse will be another side of this story. To bond a ritual to the mainland of your other routines, you need to reorganize your existing R network. New discourses result precisely from this process, from meta-level learning that begins in reflective imitation. I will use the noun production as a name for the major form of the routine, one that is an inextricable part of an R network, such as this one. The denser the routines bonds to other routines, the more productive it is. The reincarnation of a ritual into production, or the process of productization, will express itself in changes in the two conspicuous characteristics of rituals. Its occurrence will be signaled by the fact that you begin having recourse to a given procedure on your own, and you start judging the success of your performance by the product of your efforts, as if in the expectation that it may be useful to you in the future. In short, whereas ritual is procedure-oriented, production is product-oriented. It must be stressed that building new inter-routine connections is a creative process facing the learner with the need for independent decisions. We may even speak about different degrees of creativity. The further removed from each other two routines, the more creative the act of bonding them together. The majority of truly evolutionary innovations may be shown to have taken place when a connection was forged between hitherto disjoint R networks, and thus between seemingly unrelated activities and separate discourses. Mathematical literacy, the term that denotes the ability to bond mathematical routines with non-mathematical ones, involves this kind of creativity. Okay, having described the mechanism of meta-level learning, I should now proceed to the obvious question. How may this mechanism be set in motion, fueled, and made effective in the classroom? More specifically, why do some people succeed in learning mathematics while others fail? And what can the teacher do to push the learner in the right direction? These are important issues, and I hope you feel now more knowledgeable about possible answers than you were at the beginning of this unit. Although the stories you have heard do much of the necessary work, more still waits to be done. In this unit, you got acquainted with the fundamentals of the commognitive theory of learning. And as they say, nothing is more practical than a working theory, well-working theory. Still, to translate the theory of learning into a practical advice for those who teach, you must zoom even further into the nitty-gritty of the relevant processes. This unit equipped you with discursive means for this kind of additional work that needs to be done. So you may now try doing it on its own. Before we part, let me say one word about the directions the future storytelling can take. The cornerstone of the theory under construction is the assumption shared by all participationists. Even individual learning mathematics is a collective endeavor. This premise is inscribed in the commognitive tools. It can be gleaned already from the basic tenet that mathematics is a discourse. As a form of communication, discourse can only originate in a shared activity. One success or failure is thus manufactured by a collective, the learner's social niche, or even the society at large, rather than by the learners alone. To fathom the mechanism of this collective production, you would have to consider a great many factors not yet mentioned in this unit. Except for the most obvious of them, the teaching, you would have to study closely the role of students' evolving identities, the shaping impact of the culture in which learning takes place, the enabling and constraining influences of educational institutions, and the list is still long. All this amounts to an immense, partly untrodden territory, which has nevertheless been already intensively explored in numerous studies, many of them commognitive. Only to synthesize the findings so far, I would have to produce an additional unit, and probably more than one. So, although this current unit ends here, it is by no means the end of the story. I am leaving with the intention to return one day with a new season in this commognitive drama of mathematics learning. As we are talking, many of the same people who have contributed to what has been done and said in this unit are producing materials for its sequel. Let me conclude by acknowledging at least some of them. Thank you, and goodbye, at least for now.